Welcome to the session. My name is Srinivas, Assistant Professor of Physics. Today we are going to learn about equations of motion of rocket. Equations of motion of rocket. See here that present in Unit 2 Chapter 2 Mechanics of Particles. Unit 2 Chapter 2 Mechanics of Particles. This is exclusively for undergraduate students. Now we'll see first equation of motion of rocket. See there in that equation we have the terms v bar equal to v naught bar plus u relative log e m naught by m. What is v bar? Velocity of rocket, where v naught bar is initial velocity of rocket and where u bar relative means relative velocity. It is nothing but u relative is equal to u minus v, where what is u? Velocity of gases. What is v? Velocity of rocket, and log of m naught by m. So where m naught is the initial mass of the system or rocket, where m is the instantaneous mass of rocket, right? So this is the first equation of motion of rocket, and in this case especially it is absence of external force. This equation is connected in the case where external force is 0. External force acting on the rocket is 0. And move on to next equation here. Second equation of motion of rocket. See there, this is in the present of external force. That means external force is acting on the rocket. So see there, where v bar equal to v naught bar plus relative velocity into log of m naught by m minus gt, where minus gt term related to the external force acting on the rocket, right? So we know that m naught is the initial mass of the rocket and where m is instantaneous mass of the rocket, right? So now our aim is we are going to derive the first equation of motion of rocket and the second equation of motion of rocket. This is the important topic for undergraduate students, important question in this chapter. So let us see how can we derive first equation of motion of rocket, and already have seen variable mass system in which we got one equation, instantaneous force acting on the rocket. What is that? So we know that m into dv bar by dt, that equal to F external force plus F reaction force. That is, instantaneous force acting on the rocket is addition of external force and reaction force. So what is reaction force? That can be written as relative velocity into dm by dt, rate of change of mass of the rocket, rate of change of mass of the total system, right? Now let us derive first and second equations of motion of rocket. Okay, now motion of rocket. So as we know that already have seen earlier class, we know that the most mass of the rocket lies in the form of fuel. When the fuel burns, we know that gases are released through the nozzle of the rocket with high pressure. That high pressure gases will import momentum to the rocket to move upwards direction. Now we are going to derive equation of motion of rocket. So let us see, in previous chapter, in the previous session, have seen variable mass system. In the topic we got one relation, instantaneous force acting on the rocket. Instantaneous force acting on the rocket can be capital M d v bar by dt. So that equal to we got there F external, that means external force, plus reaction force. F external force and the reaction force. The instantaneous force acting on the rocket is addition of external force and reaction force. But we know that what is reaction force? How can we write reaction force? F reaction can be written as F reaction is equal to relative velocity into dm by dt, rate of change of mass. So F reaction equal to relative velocity into rate of change of mass. Now substituting in this equation, see there what we get, m into dv bar by dt. So that equal to F external force and plus u relative velocity into dm by dt. So how can we write relative velocity? Where u relative velocity can be written as u relative equal to u minus v. What is u? What is v? Where u is nothing but velocity of gases and where v is nothing but velocity of rocket. Now let us see here. Initially, here we can assume. Let us assume here, if there is no external force acting on the rocket. So in that case, what we assume here, we take here F external equal to 0. Substitute F external equal to 0 in this equation. Here let us assume this is equation number 1 and substitute F external equal to 0 in this equation. So what we get here, we get m into dv bar by dt. So that equal to so where we can get u relative into rate of change of mass dm by dt. So as we know that rate of change of velocity is nothing but acceleration. So from this one we get a bar, where dv by dt is nothing but where a is equal to dv bar by dt, acceleration. So a bar equal to, let us send m this side, then we get u relative by m into dm by dt. So from this equation we can say that acceleration of rocket is proportional to what? A bar is proportional to relative velocity, and also a bar is proportional to rate of change of mass. A bar equal to dm by dt. And again, acceleration is inversely proportional to instantaneous mass. Then A is inversely proportional to m. See there, acceleration of rocket is directly proportional to relative velocity Acceleration of rocket is directly proportional to rate of change of mass, and acceleration is inversely proportional to instantaneous mass of the rocket. Instantaneous mass of the rocket. Now we are going to derive equation of rocket, equation of motion of rocket. Let us see how can we derive that equation here. Now see here, m dv bar by dt is equal to external force plus reaction force. Now what we are assuming, if external force is 0, there is no external force acting on the rocket. So in that case, and already we know that F reaction force can be written as how much? Yes, U bar relative into dm by dt, rate of change of mass. From this equation what we get? M into dv bar by dt, so that equal to u relative into dm by dt. So multiply this equation above equation with dt on both sides, So what we get there, if you multiply on both sides, we'll get m into dv bar, so that is equal to u relative velocity into dm only we'll get. And from this one, dv bar equal to u relative velocity into dm by m. Now integrate on both sides. Let us integrate, take integration, integrate on both sides. Integration on both sides. What we get, if you take integration on both sides, we know that one constant will be added. Integral relative velocity into dm by m plus c. Now integration of dv, we know that integration of dx is x, integration of dv is v. Similarly here we get v bar equal to u relative, which is constant one, and writing outside integral dm by m plus c. And we know that integral 1 by x dx formula, we know that integral 1 by x dx can be written as log x. And similarly what we get here, applying this law, we'll get v bar is equal u relative velocity into log em plus c, So assume, so this is already earlier we assumed few equations, and here we assume this is equation number 4. And now initially at t equal to 0, m can be taken as m0 and v can be taken as v0. Right? Initially at t equal to 0, mass of the rocket can be considered to be m0 and whose velocity is v0. And substitute these two equations in above equation, then what we get there? v0 bar equal to relative velocity, and here we have to take log e, instead of m we have to take m0 plus c. From this one what we get? C is equal to, and one more thing you have to remember here, very important thing is, here mass is decreasing, right? Then in that case you have to take here, in place of dm you have to take minus dm, right? Mass is decreasing, so finally we'll get, here we'll get minus, here we'll get minus, and here we'll get minus, right? Here also we'll get minus. So from this equation what we get there? C is equal to v0 bar plus relative velocity into log e m0. Assume this is what? Equation 5. Now substitute 5 in 4. See there what we get? Substitute 5 in 4. Substitute 5 in 4. Substitute 5 in equation 4. So what we get there? See here, V bar is equal to minus relative velocity into log em and plus substitute equation 5 plus. So instead of C, we'll write V naught bar and plus U relative velocity and log E m naught. Right. So from this equation, so V bar is equal, what we get there? So V naught bar plus you take common, relative velocity common, then what we get there? Log E m naught minus log E m. So from this equation again we'll write V bar is equal V naught bar plus and U bar relative, and here we'll write this equation as log E m naught by m. So this is a very important equation. Velocity of rocket in the absence of external force. Velocity of rocket in the absence of external force. This is also called instantaneous. Velocity of rocket at any instant of time. Velocity of rocket at any instant of time. At any instant of time. At any instant of time. Velocity of rocket at any instant of time. Okay, now this equation is also known as first equation of motion of rocket. This equation is also known as first equation of motion of rocket. This equation is known as first equation of motion of rocket. So very important formula. This is the velocity of rocket at an instant of time in the absence of external force. Now again let us see, in the presence of external force, let us derive equation of motion of rocket in the presence of external force. Assume this is equation number 6. Right. See here, now the case is, now the external force is acting on the rocket. That means F external is not equal to 0. Let us see what happened in this case. If external force is acting on the rocket, already we know that m into dv bar by dt equal to instantaneous force acting on the rocket equal to F external plus F reaction force. Already we know that F reaction force can be what? F reaction force is equal to U relative velocity into rate of change of mass. Now, so what we take here, F external force can be taken as mg. How can we take? Mg, but it is acting so upward direction, that is why I have to take against to the gravitation. So you have to take F external is equal to minus mg. And here also you have to take mass is decreasing, that is why instead of taking dm by dt, you have to take minus dm by dt. So U bar relative velocity minus and dm by dt. So from these equations what we get there? So m into dv bar by dt, and substituting all these equations will get U relative velocity and rate of change of mass and minus mg. Now let us multiply dt on both sides. So what we get there, m into dv bar minus relative velocity, and here we'll get only dm minus mg into dt. And let us divide with capital M. We'll get dv bar equal to minus u relative velocity and dm by m and minus g into dt. Now let us take integration on both sides. Apply integration on both sides. Apply integration on both sides. See what we get if we apply integration on both sides. Already we know that integral dv bar, so that equal to integral right minus outside and relative velocity, and here we have the term dm by m and minus writing g outside, other integral g into dt. We'll get one constant term plus c. So applying integration, what we get there, we'll get v bar is equal to minus u, that means relative velocity, and log em. So here we'll get minus gt plus c. So let us assume, so this is equation number, already previously we assumed that equation number 6. Now let us take, this is what, equation number 7, and this is what, 8, and this is what, equation number 9. Now, so at t equal to 0, m can be taken as m naught and v bar can be taken as v naught bar. Substituting in that equation, what we get here, and we'll get v naught bar equal to relative velocity log e m naught minus g t naught. Here right, where at t equal to 0 it will become 0, and what we get finally, plus c. So from this equation, what is c? C is equal to v naught bar plus relative velocity and log e m naught. Assume this is equation number 10. And substitute 10 in 9. What we get there if we substitute 10 in 9? So where we will get v bar is equal to minus relative velocity log e m minus gt, and next term is what, this term, plus v naught bar plus relative velocity log e m naught. Then next let us about these equations. See, adjusting that equation, what we get there, v bar equal to v naught bar plus v naught bar, and take relative velocity common, and we'll get log e m naught minus log e m and minus gt. So finally v bar is equal to v naught bar relative velocity into log m naught by m minus gt. So this is the required equation for us. This equation is also known as the second equation of motion of rocket. This is the important equation. This is also known as second equation of motion of rocket. Second equation of motion of rocket. Second equation of motion of rocket. So this is the very important question in this chapter, motion of rocket. and the first equation of motion of rocket and the second equation of motion of rocket. Okay, that's all for today. We'll meet again in next class. Thank you very much.